Welcome to NASA Edge.
An inside and outside look at all things NASA.
We're very excited for the show today, and normally we'd be down in Florida covering this live.
Hot.
Yeah, very hot. But today we're back at NASA Langley Research Center. Obviously, we're going to have some pad feeds and visuals available for the rollout, so everything should be on track and good to go for our coverage today.
That's right, Blair. Over the course of the next 30 minutes, we're going to be looking at the science and technology behind Perseverance. Also take a look at the history between United Launch Alliance and Mars missions, and also see how a Atlas V 541 gets to the pad.
And of course, Mick Woltman will be joining us from LSP to talk us through that process. Plus, Franklin's going to be on the show.
That's right.
But also, it looks like we have a unique look into the lab of Jim Green as he does some last-minute modifications to the Perseverance rover. Let's check it out.
Hey, Jim, what are you doing?
Oh, just a little mission ops, a little practice before the real thing.
Jim, it's great to have you back on NASA Edge. And, it seems like it was just yesterday that we were celebrating the launch of Curiosity, wasn't it?
Yeah, I agree. Early August 2012 was when it landed. And, 9 months earlier, we launched it. It was a beautiful launch and a perfect landing.
And just almost 10 years later, we're back at it again. We're getting ready to launch a brand new rover. This time is Perseverance. Very exciting. Tell us a little bit about Perseverance.
Well, Percy is what I like to call it, but Perseverance, of course, is just the perfect name. We're continually going back to Mars. We have to persevere. Mars hasn't gotten much easier. It's still going to be a difficult landing, but that particular rover has a lot of heritage because we're using a lot of the same infrastructure that we built with Curiosity. So, for example, here is actually a model of Curiosity, but I can use it to talk about everything that we're doing with Perseverance because we took out all the Curiosity instruments, put new instruments in, and then beefed up its arm such that it could do the sampling that we want.
Now, how many different instruments are we using this time compared to Curiosity back in 2012?
Well, we have a number of similar ones, such as this laser at the top allows us to be able to hit a rock and actually start the early vaporization of that rock with this high-powered laser that then enables us to be able to get a spectrum. And this is called SuperCam. And we then have cameras, just like we did before. These cameras lay right under here. These are the mass cams. These give us panoramas and much the same view that we would see normally. And then, of course, we have several instruments on the arm. Pixel, which actually takes a postage stamp sized high resolution zapping of X-rays that then allow that material to be able to radiate and give us composition. And then in addition to that, we have Sherlock, which also has a fabulous camera called Watson, of course. What else would you name it? That particular instrument has the ability also through ultraviolet light to probe the material and get more of the mineralogy, in other words, how the rock is formed. So those are really critical instruments. And then, of course, we core rock. Here's an example of one of the cores. This actually is a granite core. It's about the size of a Crayola crayon, we'll call it, the big type. And then we put it in a sleeve, this metal sleeve, which really is well packed. We drop it on the surface for later pickup. So those are the new kind of instruments on the arm that really provide us those samples.
But one of the big differences with this rover, Jim, is that there's something special on board that might be taking off from it. Can you care explain what that might be?
That's right. Actually, there's several really special things on this rover, but one that's really new, it's a technology demonstration helicopter. Ingenuity is its name, and it sits underneath the belly pan of Percy, And after we land, Percy drops it, drives away, and then after it gets to about 100 meters away, it then radios back and actually has the helicopter take off. Now this helicopter's got cross-like blade that counter-rotates. These are about 4 feet in length, okay, both ways. So once the signal goes from Percy to the helicopter, it will go through several tests. And the first test is that it will just rise and then come down. That will be its first flight. Its second flight will be that it will rise and then move up to maybe 5 meters and then set down. And then its third flight, it will take off and move perhaps 100 meters or more and then return. And then we anticipate it will take off and actually make many more observations in a complement with the movement of the rover. This is the first time we're flying in the atmosphere of another planet. And it really is an amazing system. And we're gonna do it. You watch.
Well, Jim, thank you so much for joining us again today. And I gotta say, every time you come on our show, you always bring the best toys. Whether it's, you know, the models or the different, I think on the last show you brought a couple of cards with you. It's always enjoyable to talk to you.
Well, thanks very much. My pleasure.
The always animated and informative Jim Green. I like how NASA didn't reinvent the wheel with the body of the rover, but rather they just, you know, updated the technology and the equipment used that's going to be on Perseverance.
Absolutely. One of the things I love about the work they've done at JPL is they've actually taken that persistent platform, added all the benefits to take that extra research step, you know, to get better science, to get better results.
Yeah, and one thing that is really nice about this Perseverance rover is the addition of the helicopter.
Who knew, right?
Yeah, you know, this helicopter is really cool because back in Apollo they had the lunar buggies, and then they went to Mars with the rovers, and now they're exploring the atmosphere with a helicopter. I think that's amazing.
And it's funny you say atmosphere. We haven't really studied that, or at least flown in it with a vehicle. So groundbreaking stuff from them. But before you do that, you got to get to the ground safely. And we do that through entry, descent, and landing. And Franklin had a chance to sit down with project manager Henry Wright to talk about Medley 2, the way NASA's studying that process and making it safe.
Henry Wright, thanks for joining us today. I understand that you worked on Medley 1, and now you're the project manager for Medley 2. What data did you take from that first launch, and how was it rolled into the development of this current space vehicle?
Well, that's a really good question, Franklin. So like all things for our projects, we try and not repeat the same thing. We try and expand on what we learned. So some of the things we learned on Medley 1 is that we were actually pretty good at predicting some of our performance. So what we ended up doing was saying, okay, where are the areas where we either do not have data, or areas where the data maybe has some holes in it, or maybe quite wasn't what we were looking for. And so what we ended up doing was on the heat shield, which is the front part of the vehicle as it goes through the atmosphere, that's the part that really gets scorching hot. So we ended up scattering our temperature sensors around the heat shield in different locations so that we could understand better how the flow would be distributed across the heat shield, as well as trying to understand a little bit more about how fast it would change from one flow type to another. We also understood that our pressure measurements, which we are on the heat shield, which we use to back out how the actual aerodynamic performance is. So that's basically your lift and drag type coefficients that you hear, you know, when people talk about airplanes. And so we understood that we still needed to have our one sensor that we could use to back out what the atmospheric density is, which is really hard to measure directly. And so we have a measurement that lets us do that. But also in the lower speed regimes down near the end, when you're maybe at the last 40% of the flight, that's where we really did not have good data. And so we were able to say, let's go expand into that area. And then one of the critical things that Medley 2 brings to the table is we're actually taking measurements on the back of the vehicle. Viking in 1976 had one pressure measurement on the back shell, and we've been using that data ever since then. And it's not bad, but it's one measurement, and there's still a lot of uncertainty about that. So we added the opportunity to take a pressure measurement on the back, which we haven't done since Viking. And then we also put a bunch of temperature measurements around on the back as well, so we could then better understand the heating on the back. Keep in mind, in the back is where we'll use our models and compute what the heating actually is, and then we'll multiply by 2 or 3, and then we design the insulation system based on that 2 to 3 times number. And so by getting this information, we can actually improve that understanding and reduce the amount of insulation on the back, which gives us mass for more sensors or more instruments on the rover or anything else like that.
So now with Medley 2, this is your second attempt to gather this data. What type of data are you collecting, and how are you going to use it for future Mars missions?
One of the things that we always do as engineers is we use a lot of models or analytical tools to estimate performance or to perform part of our design. So we want to be able to analytically predict how hot something's going to be or what the forces on it are going to be. So then the other engineers can go off and do their specialty designs to decide what the insulation might look like, what the structure might look like, those kinds of things. And part of the design process is you have uncertainty. You have things you don't know. You have methods you're using that have questions on it. And so you come up with a number, but you add a factor on it. We call that margin. So one of the things that Medley 1 and Medley 2 have allowed us to do is investigate that margin, because margin is extra stuff you take to protect against things you don't know. So at the end of the day, this information is used to update our models, update our tools, so we can predict better for the next mission. And whether it's the Mars Sample Return mission that's going to go in 2026, whether it's one to Titan or Venus or any of the gas giants, or bringing things back to Earth, we still use basically the same tool set. And so by improving our understanding about the physics of the flow, the vehicle performance, how it flies in different environments, that's really where we can bring, improve our models to make things better for other missions. So at the end of the day, it's about reducing the risk and reducing the overall mass. So that's basically what we're trying to do.
Henry Wright, thank you for being on the show, and we look forward to a successful launch and landing.
All right, appreciate it, Franklin. Good to talk to you.
You know, Chris, prior to the launch of Curiosity, NASA Edge did a show on Medley, and Chris Cole and Michelle Monk back then said that they were looking to get the data from the landing of Curiosity so that they can put it into future missions like Perseverance and future manned missions to Mars.
You know, the cool thing about Medley and Medley 2 is that it was actually built here right at NASA Langley Research Center.
Yes, it was.
And speaking of data, you know, United Launch Alliance has had a rich history with launches to Mars. Boyer had a chance to talk with Isaac Spence, who is a structural engineer for ULA. Let's check it out.
Isaac, thanks so much for joining us on the show today, and it's great to actually see you in a facility there. We've been doing a lot of interviews at home, so thanks so much for joining us from the work site.
Yeah, no problem at all. Great to be here and excited to be a part of this.
Well, I tell you, we're really excited for this mission. Obviously, Mars missions are really important, and ULA has a unique history with Mars missions. Can you tell us a little bit about that legacy?
Yeah, so ULA and its heritage vehicles have actually launched every U.S.-led mission to Mars. It's 19 missions in total to date. Goes back to the Mariner 4 mission, launched in November of 1964. It was an Atlas Agena rocket launched from Complex 12 right here at the Cape. It was the first successful Mars flyby, actually sent back 21 photos to Earth. It was 6,000 miles above the Mars surface, and they were the first photos ever sent back to Earth of another planet from deep space. Fast forward 30 years, and we have a great accomplishment for our Delta II vehicle. It launched 2 missions to Mars in the span of a month. It launched the Mars Global Surveyor in November of '96. It was a global mapping mission, lasted 10 years. And then just under a month later, we launched Mars Pathfinder in December of '96. It had the Carl Sagan Memorial Station, which was the lander as part of that mission, and then also the Sojourner rover, which was the first of 4 rovers that ULA has launched. And that Mars Pathfinder mission actually sent back 17,000 images and did extensive research both in the elemental composition of the soil and the rocks, and then also in the atmosphere itself. And then now, with the Atlas V that we have, it launched the Curiosity rover in 2011, as well as 3 other Mars missions in the last 15 years. And so now here we are with the Atlas V for Mars 2020.
So I imagine there are a lot of parts to the rocket, and you have to assemble them there at the Cape?
Yes, that's correct. So the booster comes to the Atlas Spaceflight Operations Center, or ASOC, goes through initial receiving, inspection, and testing, and then it gets transported out to the Vertical Integration Facility, or VIF, and erected onto our mobile launch platform. The solid rocket boosters are our next step. For this mission, like I said, we'll have 4 solid rocket boosters. They come down from Camp Blanding, Florida, and they're hoisted and mated to the booster. Our Centaur, like the booster, comes to the ASOC first for the initial receiving, inspection, and testing, but then it actually gets moved over to our Delta Operations Center, or DOC, for vertical integration with the boat tail components and the base module. And then that vertical stack as a whole all gets transported over to the VIF and hoisted on top of the booster. Our last piece that we have is the payload. Our payload goes through final processing and encapsulation at one of our different payload facilities, and then it gets transported over to the VIF and hoisted on top. For this mission with a 68-foot payload fairing, after all of that's complete, we're actually standing at 197 feet tall.
Tell you what, it's very exciting. We're very excited for Countdown, but more importantly for you guys, another successful ULA launch to Mars. We wish you the best, and thanks so much for coming on the show.
Yeah, thank you very much. We're really excited. ULA, 139 straight successful missions, and just really excited for this one to be our 140th mission.
Well, as you can imagine, Franklin, we've been part of many launches, many rollouts. It's inevitable that we run into the delays, and it looks like there's a delay for the rollout slight. We don't know how long, but fortunately we have Mick Woltman on the phone with us, who's going to give us an update on what's happening out there in the heat. Mick, how are you doing?
I'm doing great, Blair. Before you push back, I am going to give you a heads up that I just heard that we are starting to roll.
Oh.
And I believe we do see some motion in the VIF, so we'll keep an eye on that and see if the rocket clears the doors here shortly.
We are seeing some what looks like a little bit of movement there, at least.
Oh, yes.
At least spectacular visuals here as the rocket begins the rollout process. But you talk about selecting the launch vehicle like it's this major process. I know it's important, but I mean, it sounds like ULA has got a lock on capability, and it sounds like you've done a lot of these launches successfully. I mean, how difficult a choice is it to select this? It seems like this is a perfect rocket for this situation. Was it really a choice? I guess it seems like it's just kind of a given.
Absolutely, it's always a choice. That's one of the nice things about the market right now. It's very competitive with all the commercial providers out there, and our job at LSP is to take that information and those requirements from our customer, in this case JPL and the folks that develop the rover and Ingenuity, and we look at all those requirements that they have, and then we select the best vehicle based on a lot of different things that come into play. It's part of our process that we do here at NASA to make sure that we are selecting the right vehicle for the mission at hand. So I wouldn't say lock. It's definitely a competitive market. We have a lot of missions that go on other rockets. For example, our next mission up after Mars 2020 is the Sentinel-6 MF mission out of Vandenberg Air Force Base, and we'll be flying that on a Falcon 9 rocket, which was chosen for that mission specifically for its performance and what it can do to support that mission.
Okay, you bring up an interesting point, Mick. Obviously, a lot goes into these decisions for the launch vehicles, but a lot of what motivates that decision is not just rocket performance. It's what the scientist needs in terms of where they're going, how they need to get there, the mass of the the spacecraft. So I'm wondering, how closely do you at LSP work with the scientists on their side to meet their requirements, as opposed to just getting the right power boost to a launch?
Yeah, we work very closely. It starts out sometimes 4 to 7 years prior to a mission launching. We'll start working with them on their initial requirements, and we will ask them questions. We have a survey that we start out with, and then we start working with them on the requirements they have, and we push back on some, and we look at things based on what we know about our commercial providers and what they can and can't provide. We will let the scientists know about that and work with them to define what we then end up calling an interface control document that will lay out all those requirements for the providers to look at.
Hey, Mick, I have a question that came in through our Facebook page, and that question is, what configuration is this Atlas V?
Today we're flying the 541 configuration. It is a 5-meter fairing. That's what the 5 stands for. The 4 stands for the 4 solids that are on board. The Atlas V can be configured anywhere from 1 solid to 5 solids. And for Mars 2020, we needed the 4 solids to provide that extra boost. And the 1 stands for a single engine Centaur. The upper stage can be configured with a single engine Centaur or a dual engine Centaur. Most vehicles that we launch are a single engine Centaur because that's all we need performance-wise for the robotic missions. However, for crewed missions that ULA will be working later on, they do use the dual engine Centaur configuration for manned flight.
When it arrives at the launch pad, what is the transition time? I know a lot has to happen before you've basically checked out and indicate that you are ready for launch. But what kind of time frame is that? Because as I said, normally you go out 24 hours in advance, so you just got to have plenty of time to do that. What's the timeline on that?
Yeah, it takes the team anywhere from 4 to 5 hours once the vehicle is down on the stanchions at the pad to get everything connected and ready to go. They've got to put the commodity auto couplers in. They've got to hook up the ground electrical. They've got to hook up a lot of things to get ready for launch. Because once we get to the pad, the only communication, if you will, with the rocket is via the pad systems that are here from the ASOC, the Atlas Space Flight Operations Center, where the launch team usually sits. So they control everything from a couple miles away. So they have to make sure all of that is connected and follow the procedure and take their time. So once the vehicle's at the pad and down on the stanchions, the team will take anywhere from 3 to 5 hours to finish up all that work, get the environmental control system hooked up, make sure that everything's flowing properly and the temperatures and environment are right for the spacecraft.
On the aerial view here, you can see a nice image of the top of the rocket, and you can see a list of decals from the top down, starting with NASA Meatball. Is there a special configuration or process that we use or priority for those decals or stickers? Or I guess they're not decals and stickers. I'm thinking of the kind of rockets that I get to work with, which are models.
So actually, where you are correct, they are decals and stickers. They are actually special decals that are created that will actually, they are in strips as they're put on. And as the rocket ascends through the atmosphere and we pass through max Q, they actually rip during the time. So we try to make sure that happens so that nothing interferes with the aero forces on the vehicle. But the decals are actually made to rip off. But they are a decal material. And for NASA missions, usually the meatball is the first one on top, same as if it were a commercial or Air Force mission. They would put the customer mission first, and then you come down through, you have the mission patch, which in this case, Mars 2020, and then you have the Space Force. I got to get used to saying that. United States Space Force, and then the ULA sticker and a bunch of others. Sometimes they will also have stickers just below the fairing on the Centaur stage for dedications or commemoratives of launch team members. I am not sure if we have any on this vehicle or not, but usually that order is the same for every mission.
You've mentioned so far the amount of time that's involved from the planning of these missions, talking years ago when this is developed. So it's also a lot of partners, a lot of participants beyond NASA that make all this come together. So it's not just an interesting, visual thing for the rocket. It really represents not just the time that's been put into this mission, but the vast number of people and partners that have come together to participate in this, and that is just kind of a special thing.
Yeah, absolutely. It takes a lot of people to do this. Starting at the top, right? What we're here for is our spacecraft customer. The JPL folks in this case with Mars 2020 started this science several years ago, and they got this together, and then they're trusting LSP to pick the right rocket for them, and we did, and we're working with ULA to make sure all this is mission success. So it takes a lot of people to pull this off, and it is a great collaboration and partnership between everybody to make a mission success.
I tell you what, thanks so much, Mick. We really appreciate all that you've done for us. Obviously, we love the coverage that you provided out there during Roll. We look forward to watching launch coverage on Thursday morning and joining you and Joshua Santora as you take us through launch commentary. Best of luck, and we'll talk to you soon. Good luck, and go Mars 2020.
Absolutely, guys. Thank you for having me. It's always a pleasure to work with you gentlemen. You guys are a top-notch class act, and continue doing what you're doing to inspire the next generation and share all things inside and outside of NASA. Thanks again for having me.
Awesome.
Great stuff.
And we love working with Mick. I mean, what a treat. What a brain trust.
Yes.
I mean,
yes.
Just incredible.
Man, I just wish I could be there. Seeing it, the rollout from the ground where Mick was is one thing, but to see these shots that are being provided by T-Rats, the aerial video, is absolutely amazing because we haven't always had that.
Absolutely. A big shout out to Mike Downs and his group that have provided this footage. They're providing it now. I was going to try to convince everybody I was controlling the drone, but it's foolish to do that. That group, Mike Miller and Isaac and Jamie, all those guys, they do incredible work. Right now, for us, that concludes our coverage. You're watching NASA Edge.
An inside and outside look at all things NASA.
Proceeding with the count. Status check. Go Atlas. Go Centaur. Go Mars 2020.
1, 0. And liftoff. As the countdown to Mars continues, the perseverance of humanity launching the next generation of robotic explorers to the Red Planet.